Hello, everyone, and welcome to phyloseminar.org. The current theme is evolutionary ecology, and this is the second talk in a series and 3 talks on that topic. Please use the YouTube live comment box to ask questions. Today's speaker is Wade Dismukes, a graduate candidate in Tracy Heath's lab at Iowa State University. His dissertation focuses on developing new methods in co-phylogenetic analysis. He is interested in exploring the uses of machine learning and phylogenetics, particularly in biogeography and host symbiont evolution. Welcome, Wade, and thank you for participating.
And thanks, Eric, for the kind introduction. Like Eric said, I'm a graduate candidate, so this is talking about a couple of chapters of my dissertation, including one on machine learning. And also, just as sort of an advertisement, be sure to check out Chris Wheat's talk in this series. It's already up on YouTube, so you can watch that. And then Mariana Braga's talk is in a couple of weeks, and it's going to be really cool on ecological networks. So I'd highly recommend both of those in this series on evolutionary ecology. So my work mostly focuses on developing methods dealing with host symbiont evolution. So symbioses are prevalent throughout the tree of life, with stunning examples of highly specialized symbionts like this leaf flower moth, as well as other pollinators and the lice that could be inhabiting the fur of this pocket gopher. And this sort of tight correspondence, this host symbiont relationship, has always been of interest to evolutionary biologists, even since Darwin. But the question is, how did these highly specialized systems evolve? So we might take our pocket gopher as sort of a nice example. So if we imagine a species of louse living on a species of gopher, when these gophers get together to mate, the lice have an opportunity to switch gophers and mate as well. And this gopher switching allows genes to flow through the louse species. And so if we continue that sort of logic, these lice have very few opportunities for gopher switching. And so when the gopher speciates into gopher A and gopher B, the lice will also speciate into louse A and louse B, sort of a geographic isolation, because the gophers serve as a sort of island for the louse. So if this happens repeatedly, we'll actually get matching phylogenies. So you can see that these evolutionary trees are perfectly concordant. This is sometimes called Fahrenholt's rule, after a German parasitologist from the early 20th century. And so this is sort of what we imagine might happen. But in reality, we don't really see that perfect matching. So we have these same gophers and lice, and this is a real data set from a classic study by Mark Hafner. And so you can see that these trees are similar, but there's still a lot of differences in them. And so the question is, how do we try and figure out why these trees are discordant when our prior knowledge we might expect them to be more similar? And so we might think of different events that could happen to explain this. So I talked about co-speciation. So that's speciation that occurs when that gopher goes from gopher A to gopher A and gopher B, and the louse also goes from louse A to louse B at the same time. That's called co-speciation. We also have things like host switching. So the symbiont, the louse in this case, might switch. It might speciate and then switch to a new host that it previously wasn't using. So it might look like this, where this switches down to this host. We also have symbiont speciation that occurs. So this is another way to explain this additional tip in the symbiont tree. So there's more than one explanation for these different scenarios, where we might have the symbiont that speciates. And then, of course, we can have the symbionts going extinct or losing that interaction. And so we could take this, these sort of events give us a framework for trying to understand this. And there's 2 general methods people typically talk about when they talk about reconciling the differences in these trees. One of these uses these events directly. It's called an event-based method usually. And so in this type of method, we're attempting to map the symbiont tree onto the host tree using these events. And so we assign each of these events a cost, and we try and map this symbiont tree onto the host tree using these events. And so once we do that, once we get a full map, we add up all those costs, and we repeat this whole process until we get a mapping of symbiont tree to host tree that is the lowest total cost. So this is sort of parsimony-like approach. This is probably the most common approach you'll see, or one of the more common ones. One of the issues with these methods is, while it gives us this nice mapping, assigning these costs is, in a biological meaningful way, can be quite difficult, as well as other issues that parsimony has, like there might be more than one lowest cost mapping, and there's no clear way to estimate variance in this case. The other type of approach is called global fit, and this is where we're trying to get an overall measure of concordance between the host and the symbiont phylogenies given these associations that they have, these ecological interactions. So this is, I'll just give one example here, but these all use sort of matrix algebra as sort of the basis for them. And so in this case, we convert our host and our symbiont tree into phylogenetic distance matrices. We then calculate the principal coordinates of those and then do some matrix multiplication here. That's so what this is showing to get this D matrix. And then with that D matrix, we can get this sort of sum of squares type value by taking the trace of that matrix and then squaring that. And this gives us, if we did this on our gopher lice example, we'd get one value of this. And then we could measure the overall concordance using hypothesis testing by randomly shuffling the rows of this association matrix and recalculating this value to get a null distribution.
So let's, so I know this isn't the main focus of your work, but this is just interesting. So with what's being fit here is the A matrix, and we're trying to minimize this trace square.
Yeah, exactly. So, so this, and that's because the real hypothesis test is trying to measure whether these associations are just random or not, pretty much.
But it's just interesting to like be taking your tree, boiling it down to a matrix. That seems reasonable, but then principal coordinates on a distance matrix, I'm not sure what sort of properties that has.
Yeah, and that's actually interesting that you bring that up, because I bring this statistic back up later. So
okay, well, thanks.
Yeah, so I think the intuition you have about what this is measuring is a pretty good intuition. So we have these two approaches, but neither of these gives us a nice generative model to describe what's going on during this process. So I developed one. This is called the Cophylogenetic birth-death model. This is based on a very basic birth-death machinery. And this is available in my R package, TreeDuckin. There's a paper about it too, if you want to check that out. So with this model, we start with one symbiont in yellow and one host in blue here. And then we have an association matrix that describes their interactions as we're going to go through this, birth-death model from time 0 to time t star. And so we're going to draw times based on the rates of different events we have. And these events are the same that we discussed when we were talking about event-based models. So we're going to randomly draw events until we reach t star. So we randomly draw some amount of time. We get a host speciation. And so host 1 here in this column is going to turn into 2 columns. It's going to turn into H2 and H3. We can repeat this process. And this time we get symbiont speciation. So same as before, except now we're dealing with the rows of this association matrix. So S1 is going to become S2 and S3. And you can see that the symbiont has inherited the range of its ancestor. For the host can have lineage sorting occur. So it can inherit one symbiont or another or both. But the symbiont always inherits the ancestral range of the ancestor. So we draw another time, and this time we get co-speciation like we had before. And so we randomly choose one of our hosts, and then one of the associations with that host. In this case, we got H2. And one of the associations, we randomly got S3. So H2 and S3 are going to co-speciate. So these become H4 and H5 and S4 and S5. And then the remaining associations they have are randomly sorted among their descendants. So we can continue to do this. We can also have anagenetic events. So I've only included dispersal in this example, but we could have extirpation too, where they lose an association. So there's no branching that's going to occur. So no change in our trees other than more time. But this S5 has dispersed from being only on host 5 to host 4 and host 5. We could also have H5 being lost, or any sort of combination of events like that. We could also have a host switch speciation event. And so this is occurs when a symbiont speciates and one of the descendants retains the ancestral host range and the other jumps to a new host. So this is very similar to jump dispersal from historical biogeography, actually. And so that's what this will look like. And then, of course, we also have extinction to deal with. So we have symbiont extinction. So in this case, S5. So this row is going to get deleted from our association matrix because that symbiont is dead and so isn't interacting with anybody. And so we get this 3x3 matrix. And we continue to do this. We get host extinction this time. And you can see we lost host 4. So that's a column. And S7 here is now left with no hosts. So that means symbiont 7 also goes extinct because the symbiont needs a host to persist. So that's coextinction. So finally, we draw our last time and we hit that T star. Currently, we only have a way to simulate this to a set time. I haven't delved too deep into different algorithms for trying to simulate to a set number of hosts or a set number of symbionts. That's definitely an area of future research for me. And we end up with this kind of uninteresting 2x2 tree if we prune off our extinct tips. And so, like I said, this is sort of an uninteresting example. Most of the examples you're going to see from this are going to look more like this, where you have lots of tips and lots of events. So each of these colors corresponds to a different event that occurs, with purple being co-speciation, for example, and a number of other events that can occur. So we have a bunch of these events, and we'd like to figure out how often they occur in empirical examples. But before we can do that, we sort of need to step back and see if there's other approaches to do this. And there are, but I'm going to attempt to use machine learning to count the number of events in a cophylogenetic data set like this. So this is often called a cophylogenetic data set. And so one approach that people have taken in the past is to try and use ABC to do this. And so I'm going to build on this approach. Basically, where you take this cophylogeny, you turn it into a network or a graph, and then you calculate a bunch of different metrics on that graph. And so while this is a nice approach, it does have some caveats as it doesn't, it has the normal constraints that ABC typically has, like the issues with dealing with the cursive dimensionality and that sort of issue. And so I'm going to try and take a machine learning approach. And this word is everywhere these days. So I'm going to try and unbuzzwordify it. And it's usually broken down into these 3 flavors. I'm going to be specifically talking about a specific type of supervised learning, but there's also reinforcement learning and unsupervised learning. And if you want to know more about these, there's actually a series of talks on machine learning in the phyloseminar series that I recommend you check out. These are from last year and they're all up on YouTube. So I won't be going super duper in depth into the mathematics behind machine learning, as this is not an area of expertise, particularly for me. But I'd highly recommend any of these talks. So like I said, I'm going to be focusing on a type of supervised learning. And the type of supervised learning I'm going to talk about is a neural network. So here I have a very simple neural network where we have our inputs in red here and our outputs. And we're going to do something to convert our inputs into output. So if this were like a regression model, say, we might have y here and a number of x variables here. And I'll explain this black box that this blue layer represents using an example. So for a simple case, we're going to try and predict the age of individual abalones. That's shown here, and that's the abalone over here. So we have all these different measurements of this. This is sort of a classic example of machine learning. And we have this big data set where we have these parameters, and we also have the actual age of the abalone. And the reason we want to try and estimate this is as a proxy, because estimating the age of these is very labor intensive. And we're going to split our big data set up so that we have a training data set and a validation data set. So we take our training data set and we input it into our model. So each row of our input data gives us some value for these parameters. And we want to see how these values can help us predict this age of an individual. So for each of these blue nodes, we have an arrow that leads from each of our inputs. We can assign each of these edges, these arrows, different weights, and then we can take a weighted sum of our inputs here that's going to go into this blue node. The blue node represents this activation function. In this case, we might use like the ReLU or like a sigmoid function. And this will activate if it's over a certain value and then influence the estimate of age. And then we can evaluate how well we estimated age by comparing this predicted value to the true value. And we could do this using some sort of loss metric like mean squared error. So we do this for all of our blue nodes, and then we shuffle our data and go through these epochs. Once we go through all of these blue nodes for all of our data, so we do this for this set, and then we do it again for each row of our data. That's one epoch. And we repeat this for a number of epochs by shuffling our data set so as to randomize the input data. And so the learning part comes in when the model adjusts these weights that are associated with these edges to try to improve our estimate. And after we're done with this training data, we could show our model data that it hasn't seen, that we set aside that validation data set to test how well it does on new data. And so we could even take this a step further and add additional blue layers, which do the same thing, where we have this these weights associated with each of these arrows. These weights go into this activation function, which tells us how to activate different neurons. That's what these nodes are called, until we get a nice estimate. Again, this isn't my area of expertise in particular. So I'd recommend some of last year's phylloseminars if you're curious about the mathematics behind it. So the question is, how can we use a method like this to count the number of events in a cophylogenetic data set? So we could take a page from that ABC approach and take graph summary statistics or graph metrics. and use these as input data for a number of events as output data. And then we can use this same multiple layered or deep learning, deep neural network. So we can get these graph summary statistics en masse because we have the simulator from TreeDuckN. And so we can simulate a bunch of cophylogenetic data sets using TreeDuckN, with our purple here showing ecological associations, and our host tree on the left, and our symbiont tree on the right. This cophylogeny then can be input into a different R package, iGraph, to convert it into a network or a graph. And then where we have red showing those same purple lines, and black showing the symbiont tree, and gray showing the host tree. And we prune off all our extinct tips just for simplicity. So then we could take our graphs and calculate a bunch of summary statistics from this, like diameter and centrality and modularity. We can also use, for example, that parafit trace value that we discussed earlier to see how well this corresponds, how well this value might correlate with our estimates of our different events.
So just to be clear, these summary statistics are really just having to do with the graph as such. It's not like there's no distinction between like the red edges, like you're not telling it like these are two trees that are connected by a collection of lines.
Yeah, there is no telling it what it is. We're feeding it into this software, and it does label the different edges. So there's different ways we can calculate different parts of the graph and stuff like that. But it's sort of this abstract version of these statistics.
Okay, thanks.
So first of all, we should see if this works with simulated data. So I performed a simulation study where I just simulated everything to a time of 1 with no extinction or extirpation, trying to see if we can accurately measure multiple events using a deep neural network. And I did this varying a few different parameters, including co-speciation and that should say host switching. Co-speciation, and then there's also one treatment that has co-speciation and host switching. And so for each of these, we also have a value of dispersal. So that non-branching dispersal event that occurs. So this adds some noise to our estimates of co-speciation and our estimates of host switching as well here. And so for each of these, we have 0, 1, and 2 dispersal rates. And so we simulated 1,000 cophylogenetic data sets. So this is pretty preliminary for now for these 6 treatments. I'd like more data for sure than 1,000. But so for these 6 data sets, we have 1,000 cophylogenetic data sets that we're converting into those graphs, calculating those summary statistics, and then inputting into this deep neural network. And so this is what my graph looks like in sort of an abstract sense. So we have our graph summary statistics over here and the number of our different events that we're varying on the right. And I used 3 layers, each with 64 nodes. There's definitely a lot of room for experimentation here and improvement, I think, as I continue to work on this project. Like I said, it's pretty preliminary. So trying to figure out the exact perfect number of these is something I would like to play with a little bit more. And I used 200 epochs to do this. And then I evaluated this all using mean squared error. Okay, so how well did it work? So this is the graph for the co-speciation data set with no dispersal. So this is sort of the simplest case. So it's only co-speciation, no dispersal. And you can see that our model loss is plotted here on the Y. So this is that mean squared error. And then each epoch, we've calculated the model loss to see how quickly it's learning. And you can see that it decreases very quickly and then sort of levels off. And then at the end, the validation set starts to get a little above that. I think that looks like under training to me. So I'll probably like to get more replicates, and I think that will likely go away, but we'll see what happens. So I did this for all of the data sets. And you can see a very similar pattern in all of these cases where we have the approaching of towards some particular value that's much lower than where it started. But if you look at the scale, there's quite a bit of difference. So you can see the loss is much higher when there's host switching added into the mix, and it's higher when there's more dispersal, which makes a lot of sense because there's more events, there's more noise that could affect the different, the trees get more complicated with more tips and that sort of thing. And so it goes from low dispersal to high dispersal here. As for how well it predicts the different event numbers, it does a pretty good job, I'd say. So if we look at this graph here, so again, this is that simple case, and I'm going to walk you through this and then show you the all 6 treatments. So on the y-axis here, we have the predicted values, and on the x-axis, the true values. And you can see that it lines up with this one-to-one line pretty well, at least for lower values. I think I'd like to graph the tree size against mean squared error to see if we just get more loss with bigger trees, which I think is probably what's happening, but I didn't have a chance to do that before this talk. So that's going to have to wait. And so we see a pretty good trend for all of these cases with co-speciation. It does a pretty good job of measuring the number that's going on, particularly at these lower values, but also it does pretty well, even in the most complicated example here with just high dispersal and host switching and co-speciation. So it seems to do remarkably well, I'd say. So we could look at the other graphs too. And so looking at host switching, we can see here on the top row, if you look closely, there's a dot here. That's actually 1,000 dots, all at 0. So it's not measuring any host switching that's going on. It's approaching 0 for all 3 of these top ones, which is nice. It's not measuring something that's not there. That's good to know. And then on the bottom row, we seem to do, again, a pretty decent job of estimating the number of host switching that's going on in these data sets. Where we get, so this is the same value of host switching. So it might be interesting to increase the number of the host switching rate to see if we get a more dispersed away from this one-to-one line. Okay. So we can also look at dispersal. It seems to not, so this is the case with 0 dispersal, like before with the host switching. And with 1, dispersal values of 1, it seems something odd is happening there, but otherwise it seems to be doing a pretty decent job. And you can pretty clearly see that, as expected, these higher values of dispersal have more dispersal going on, and they're predicting higher values as well, which is very promising, I'd say. So one other thing I was interested in, and I think this will be useful to go back to and try and explore why this might be happening, is if we compare our parafit statistics. So I thought maybe this would be a really informative statistic because maybe it's measuring co-speciations in a weird roundabout way. But when we look at this, it doesn't seem to be doing a very good job at all. So this is the co-speciation case where we have no host switching and no dispersal. And on the y-axis, I have plotted the predicted co-speciation. On the x-axis, I have the value of that parafit statistic that I input into the model. And it's not making a very good one-to-one graph at all. So that's quite interesting. We could look at this across all of the samples. And again, it doesn't seem to have any particular trend. It does seem to have some sort of increase here, approaching this one-to-one line for all three of these host switching ones, but it doesn't look like it's measuring a whole lot. So I'm not sure why exactly that might be occurring. I'd be happy to discuss that further with anybody. But it is pretty interesting that despite this, a lot of times this parafit statistic it doesn't correspond with any event, but it does seem to do a good job of testing that hypothesis of whether these associations are random or not. And so in conclusion, first pass on this preliminary result, it seems to work pretty well. I was pretty surprised that it worked as well as it did. But I think I need more replicates. And there's a pretty low model loss on some of those different scenarios. So I'd like to work on the model a little more, tinker with it a little bit, and try and bring that model loss value down a little further by maybe introducing more layers, more of those different blue layers I talked about earlier, or adding more neurons into those layers. There's a lot of ways that I could do that, explore how that could be done. And then looking a little more into this parafit statistic, it doesn't seem particularly informative, but maybe I'm missing something. It's very likely I am. So I'm very curious what's going on in that case. Okay, so this is a really simple example, sort of the simplest, and it's only using simulated data. So there are a number of different things we could look into. Which features are the most informative? Which of those graph statistics correspond? Which of them are giving are giving us the most signal for our different events? How does this compare to that ABC approach that I talked about before? So I could do a pretty direct comparison, I think, between the two. And so I also had turned off extinction. And I think extinction would do a lot to derail the model, to sort of introduce a whole lot of noise into the model and maybe throw off the signal quite a lot. And so these are some of the next steps for this project before I finish my dissertation, hopefully. And trying to really figure out, get to the bottom of this. And then, of course, probably of most interest to empiricists, how can empiricists use this? So I need to figure out a way to make it really relevant to empiricists and to input empirical data into this model to have it predict these numbers for empirical data sets. And then future work, I'd like to include other data into this model, like biogeographic or trait data, particularly traits that mediate these ecological interactions. There's a lot of examples of this. So those lice that I talked about earlier with the gophers, their body size is actually correlated with the hair width of the species of gopher that they specialize on. So there's a lot of that sort of specialization going on in these cases. And that's really interesting, and it probably provides a lot of information about these events and what's going on in these systems. As well as biogeography can also cause very similar patterns in this data. And so trying to tease apart who's the whodunit of, like, is it biogeography or is it cophylogeny or both? And how do we figure out which is which? I think that's a really cool question that I'm really interested in exploring in the future. And so with that, I'd like to thank my lab, particularly my advisor, Tracy Heath, and also the NSF for money in Iowa State, and also, of course, Eric and Mariana for inviting me to give this talk. And I'll take questions in the YouTube comments, I think, right?
Yeah, well, I can. Thank you very much, Wade. That was awesome. So I'll just read them off. So Mariana says, really cool talk. I'm a bit bothered by the coextinction. Do you think it would complicate things too much if you added a probability for the parasite to disperse when its host goes extinct?
I think that's very manageable to add to the model. I like that idea too. I definitely included the coextinction as sort of a simplistic case, starting with this very simple case. But I think that would be a really cool thing to include, this sort of like escaping death type scenario. It's really a cool, and I think probably not uncommon for these systems.
Su Hao Kuo says, cool method. I guess the method requires a matrix of features as the training data. Could you talk about how you encoded tree pairs into a features matrix?
Yeah, so I sort of, I guess, cheated a little bit by converting my trees into graphs and then summarizing those graphs using these statistics. You could probably start with just the trees and summarize them in various ways, but there's not a lot of different statistics you can calculate that deal with this host parasite stuff outside of these global methods. So,
but I do wonder, like, what if you couldn't you like just use the parsimony score as one of your input, like one of these sort of host parasite parsimony things?
Yeah, I think you could. I think that would be pretty cool. I think that you could input it into one of those parsimony methods and then use that as a training data as well. I think that would be that's reasonable to me. At least it gives you some sort of estimate that the model can use to train.
Yeah, and I mean, I just wonder if maybe like even if you could use like parsimony scores for like a variety of different settings of like different costs for different types of events that happen on the pairs of trees. That would seem pretty informative.
Yeah, I think it would be important to include time in there because some of these event-based methods don't require time trees, and so it can be a little weird when you have two trees that are different lengths and you input them, and that's sort of a qualm I have with those.
Yeah, methods. But I mean, I mean, you're building a black box. Like, it seems like throwing more things into the black box is not a bad thing.
Yeah, and I should mention also that I didn't use very many graph theoretic statistics. I could probably throw a whole lot more in there and see if it improves the estimates. So, or particularly if it lowers the model loss, I would expect. But
yeah. Did you? I mean, I guess there's this general concern with machine learning methods of like domain shift, where you sort of have everything set for one domain, like one set of parameter regime, and then you move to a slightly different one, and then all of a sudden your model just does something completely crazy. Did you think of this? I mean, even things like tree size is something like, for instance, if you train on a bunch of medium-sized trees, then you get a small tree or a big tree or something like that. That can throw things off.
Yeah, that's something that while I was doing this, I was like, wow, I really hope that's not what's happening. But it's not something I've investigated in any sort of deep way. I think that maybe randomly drawing from a really big list would be the best. So maybe just inputting like a ton of data might be the best approach. You do get a very large variety of trees. So I said there were about 1,000 in each one. And the reason there's about 1,000 is sometimes you get these two-chip trees where you can't really do much with them. So they get thrown out.
Yeah.
And so there's definitely this like big distribution of different values. And I think that's definitely something I want to explore, is how the tree size might have this error estimate, which I expect it probably does quite a lot. So,
I mean, one thing you can do, I mean, I think it's always important to calibrate your simulation. I mean, it sounds like you've got an awesome simulator. But I guess, I mean, you can sort of calibrate it by taking a bunch of empirical cophylogenies and taking your summary statistics and making sure that basically like the joint distribution of the summary statistics on the real data sits sort of in the distribution of the simulated set.
yeah, I think that's definitely something I should do. That's a really good idea. I actually write that down.
So while, let's see, so Noah, I'm sorry, I think it's Legal. Great talk. I was curious, do you think your model will hold up in the case where sampling is low in terms of population size or temporally, or will there be deviation?
I am unsure, but I think we could test that it's pretty reasonable to test that, at least the sampling bias. So if we hide a bunch of the samples, we'll be able to measure how big of an effect that has. I think looking at how extinction affects it will really tell us how big of a problem that is, because another way of thinking about extinction is those are just all species we haven't sampled. So because we're going to have to prune them off at the end anyway. And so there's all these problems like having a host switch that's from a lineage that now is extinct. Like we have like transfers from ghost lineages and stuff like that that can cause all sorts of mayhem in our estimate. So I think that probably is a very big problem. Yeah.
Just one other thing that you might consider, there's like a literature that uses graphs directly as input for neural networks. So the original version is something called message passing neural networks, and they use this to great success in predicting like chemical structures. Like sort of properties of chemical structures. But more recently, and I think more relevant to you, there was I think it was an ICLR paper that is called DAG-NNs, like directed acyclic graph networks. And you have a DAG here, and basically it like you have information sort of flowing down the graph and then back up the graph, and you have these sort of operations that aggregate information. I'm not sure that would. I mean, your results are already very good, so maybe it's not worth it. But I mean, it might be worth at least looking into.
No, I think it's at least worth exploring, for sure. Because it sort of gets us closer to the idea that we want to be like, there's more information in the graph itself than these summary statistics have. So
yeah, at the same time, like I do wonder if you could do just as well with sort of some summary statistics, but it also, in particular, summary statistics that like take into the account the fact that you have a cophylogeny and not just a generic graph.
Yeah,
that sort of would be my. I mean, these things will be a little bit. I mean, I think they've got software up for doing them, but I mean, that'll be a little bit of effort to do.
Sure.
But that's very cool. Right on. I don't see any other questions, and that's all for me. So maybe we should say thank you very much.
Thanks again for allowing me to do this.
Yeah. Next is going to be Mariana herself.
Yeah, definitely check out Mariana's talk.
Great. Thank you.
Thanks.